live stream. I know it's finals week for a lot of people. Maybe next week is for you. Either way, I wanted to help you get ready for finals. So figured I'd do a little extra live streaming this week. Hopefully I'll be doing another one this week, maybe tomorrow or possibly Friday. So be sure to hit that subscribe button down below and hit that bell icon and turn on notifications so you know when I'm going live. But today I just wanted to go over a couple of topics here with you. As always, if you have any questions along the way, please drop those in the live chat. I'll do my best to answer whatever questions anybody has, even if they're not on topic. I'm always happy to help answer whatever questions you might have that aren't the questions I'm talking about. So be sure to drop those in the comments as we go through these topics and example problem that I have prepared for you. And if you find this helpful, please be sure to hit that like button as well. It's the best way to help kind of spread these videos out to other people so we can keep growing the Jake's Math Lessons community and help as many people as possible. So without further ado, let's go ahead and jump on into the topics that I had prepared for you guys here. So first of all, one thing that I wanted to go over and talk about with you is continuity and what it means for a function to be continuous at a point. And, by extension, what it means for a function to be continuous in general, or continuous over a range or everywhere. So just wanted to kind of start out here with what the definition of continuity is, or the definition of a function being continuous at a specific point. So in general, some function f is going to be continuous at a number a. So basically we're looking at the point where x equals this number a. And I'm sorry, let me adjust my settings here. All right. Yeah, that looks a little better. So in general, we're thinking about what it looks like for some function, some unknown function f of x, and trying to think about basically what it means for this function to be continuous at the point x equals a. So what we're, basically in this kind of equation here, this definition, you need to keep in mind that a is actually a number. Even though it is a letter, it represents some constant number. It's not a variable like x is. So for a function to be continuous at this point, x equals a, that means that we would need the limit as x approaches that a value of our function f of x to equal f of a. Well, what does that mean? Basically, all that really means is if we have, you want to kind of think about, well, let's think about each side of this equation separately. So we have this limit over here on the left. What this is saying is so imagine we have some function. Let's just say, we'll kind of graph it here on a XY axis and think about what's going on here. So let's just say we have some function that looks something like this. Okay. So this function is, let's just say we have some a value, which will go right here. We'll say this is x equals a. So basically what we're kind of looking at here is what this function looks like specifically at this x value here. So if you go to this x value, x equals a, and kind of trace that down to our function, we're basically looking at this point right here. We're trying to figure out if this function is continuous there. Well, this left side of our equation here, the limit as x approaches a of f of x, what that's saying is, as if we imagine kind of traveling along our function from both sides, as we get closer and closer to this x value of a, so as we kind of travel down our function here, and then travel along our function from the left, as we get closer and closer to this x value of a, what y value are we getting closer and closer to? So what y value or what output of our function are we approaching as our x value approaches that a value? So the kind of important thing to point out here is limits don't really care what's happening at that specific point. Limits in general only care about what's happening around that point. So this left side of our equation, this limit, it really doesn't care what's going on our function at this specific x value of x equals a. What it cares about is what's going on as we get really, really close to that x value. Kind of imagine walking along your function or traveling along your function. As our x gets really close to that a value, what's going on? And what that's going to tell us, this limit, is what y value we approach as our x gets really close to that. Well, kind of the flip side of that is what's happening on the right side of our equation here. So the right side of our equation just says f of a, which just means the output you get from plugging in this input a for x, which literally is just going to give us the y coordinate or the y value of this point right here when x equals a. So that would give us this point here. So basically the idea is if a function is continuous at this value of x equals a, that means you get the same thing whether you approach that x value from either side or by simply plugging that x value into the function. So basically what's going on around that x value lines up with what's going on at that x value. So that's how you can kind of think of what a continuous function means. If you want to think about what that actually means in terms of, kind of the simplest way to visualize it is if you can draw the whole function without picking up your pen or picking up your pencil. So basically what that means is there's no holes or jumps in your function. Like in this case here, there's no holes or jumps. And as a result, as we get close to some point, we get the same thing as just going to that point on the graph. Alternatively, if we think about a function that's not continuous, so let's say we have a function instead that looks like this, and let's say this is our a that we're looking at, and then we just have, so basically this function that is, it has a hole right here, and then instead of the function being defined at that point, it has just this one single point up here. So this function is defined for all x values. You can kind of imagine this going on infinitely in both directions. There is this hole here, but the function is still defined at that point because we have this extra point up here. Well, if you think about what happens as we approach that x value from either side, as we imagine kind of traveling along our function from the left and then traveling along our function from the right, the y value that we approach, that we get really, really close to as our x gets closer and closer to this a, is right here, right? Basically just horizontal from where this hole is. But if we just look at where the function is actually defined at that point, that puts us up here at that actual point. So that would give us something up here. So basically the limit as x goes to a of f of x in this situation over here on the right, that limit is going to give us a y value down here. Whereas on the right side of our equation, just plugging in a into our function f is going to give us an output up here because this is where the actual function is sitting. So since those don't line up, this function is not continuous at x equals a because we're not approaching the same point that we actually have on our graph there. So that's really all it means for a function to be continuous at a certain point, and kind of what that looks like graphically. So I do see some questions here. Let me take a quick peek through the comments before we move on to the next topic here. Awesome. Yeah, thank you. Really appreciate the nice words there, Tucker. And I'm glad I've been able to help you. It's great to hear. Love hearing stuff like that. So appreciate you sharing that. All right. Let's kind of build on this topic of continuity and what it means for a function to be continuous. And what we're going to get into now is the intermediate value theorem. So this doesn't, necessarily directly build on continuity, but an important condition of the intermediate value theorem is that the function is continuous. So I wanted to kind of touch on the continuity first. But basically what the intermediate value theorem says is if we have some function f, and I'm going to just kind of tell you exactly what the theorem says to start, and then I'll get into explaining kind of visually what this looks like and what it actually means. Because I know a lot of times when you're reading theorems or different things in calculus, it kind of sounds like nonsense. So I want to be sure to kind of explain what this really actually means in English instead of in math. But what the theorem actually says is we have some function f, which is continuous on a closed interval from a to b, and we have some number n, which is any number between f of a and f of b. We need to make sure that f of a does not equal f of b for this to work. Then, based on knowing that this stuff is true, there must exist a number c in the open interval a to b such that f of c equals n. So what does this mean? Well, really all this is saying is we have some continuous function f, which is continuous on an interval. It doesn't have to be continuous everywhere, but we need to make sure that it is continuous on some closed interval. Where if let's kind of actually show what this looks like graphically. That's probably going to be the easiest way to make sense of this. All right, so we have our x and y axis here. And let's just say we have some function which we know. So let's kind of think about what conditions we have here. We have some function that is continuous on some closed interval from a to b. So let's just say that we have some interval like this from a to b. And our function is continuous on the closed interval. So we know it's going to be continuous all the way up through those points, basically. Let's just say something like this. Actually, not quite like that. Let's go like this. Let's just take this for example. So this is a function that is continuous over this whole closed interval from a to b. And we have some number n, which is between f of a and f of b. Well, f of a and f of b is just saying whatever output you get when you plug in a and b into this function. Or in other words, the y value of whatever your function is at these 2 points a and b. So basically this right here is f of a, and this right here is f of b. It's just the point that lies on this function at these x values that we're looking at. And then we have some number n, which is between them. So we know basically that n has to be somewhere between there and there. So it could be anywhere in here. We know, based on the intermediate value theorem, that there must exist some number c between a and b. So then there's some other number c, which is between here and here. So let's just say right there, for example. Or, it kind of works the other way. So we would need to pick our n first. So let's just say our n is here. Anywhere between these 2 points on the y-axis, basically. And we know that there has to be some number c between a and b, where if we look at our function at that x value of x equals c, we can get the output of n. So basically what this is saying is if we know our function's continuous, we know that our y value of our function at these endpoints here of a and b are not equal to each other. Basically, that's saying there's a possibility to pick some number between those two outputs, those two y values. And since we know the function is continuous, no matter what n we pick between here and here, there's some x value that basically we can plug that x value into our function to get this n as an output. So in this case, you can see that it would be right about here. We can plug this c value in here into our function, and that'll give us n as an output. That's not a very straight line, but hopefully you can kind of get the idea there. No matter what n we pick between f of a and f of b, there's going to be some c between these a and b values where we can get that n as an output. No matter where we pick our n, let's say we pick an n here, we're going to be able to get some c value between a and b that we plug into the function and get that as an output. So that's really what the intermediate value theorem is telling us. And that's all built on and contingent on the fact that our function is continuous over this whole interval of a to b. If it's not continuous, then it's not going to really be applicable. The intermediate value theorem won't really tell us anything. So we need a continuous function. So why is this important? Well, this has some valuable information that we can gather about a function that we know is continuous on some closed interval. So for example, I have a example problem here that kind of shows you how this is helpful or what you can do with it. So let's say we have this example here. we have we need to use the intermediate value theorem to show that there is a root of the given equation in the specified interval. So basically we have this equation here, and we need to show that there's a root, or in other words, there's a solution to this equation. There is a point between this interval here, between 0 and 1, x between 0 and 1. There must be a point where the cube root of x equals 1 minus x. Well, to use the intermediate value theorem, what we need to do is kind of think of a couple different adjustments that we can kind of make to this problem. First of all, a root kind of implies that there's a point where we have a function that equals 0, right? We don't really have anything equal to 0 here. So what we probably want to do is basically add or subtract everything over to one side of the equation. So let's just say we will subtract the cube root of x from both sides. And we'll get 0 equals 1 minus x minus the cube root of x. So the reason why we wanted to do that is now we can think of this right side of our equation here as our function. So we have some function, f of x, which equals 1 minus x minus the cube root of x. And we want to find a root of this function between x equals 0 and x equals 1. So where does the intermediate value theorem come into play? Well, we need to first of all make sure that this function is continuous on this whole interval from 0 to 1, which really all three of these pieces of this function, 1, negative x, and negative cube root of x, those are all continuous everywhere. So as a result, this entire function is going to be continuous everywhere. Cube roots are fine to take. It's fine to take the cube root of a negative number. So we're not going to get any issues here with taking a cube root of x. But, you know, even if that were an issue, 0 to 1 is obviously not, there's no negative numbers in there. So everything between 0 and 1, this whole function is continuous. There are ways that we could prove that, but I'm not going to get into that here just because this problem specifically tells us to use the intermediate value theorem. As a result, I think it's reasonable to assume that this function is continuous based on how the problem is telling us to solve it, because the intermediate value theorem needs the function to be continuous in order to actually use it. So let's just go ahead and, you know, assume that this is continuous within this interval, at least. Basically, let's kind of think about this piece by piece here. Thinking about what the intermediate value theorem tells us. It tells us that we have a function, in this case, that is going to be continuous on the interval of 0 to 1. And we want to look at, basically, kind of looking back here to the intermediate value theorem, we want to look at basically the endpoints of that interval. So f of a and f of b. So if we think about, in this case, f of a, which is 0, and f of b, which is 1, we want to figure out what these two values are, because intermediate value theorem is going to tell us that there has to be a place on this function, this continuous function, where we can basically obtain any output between whatever these two outputs are, and it's between the inputs of 0 and 1. So let's just figure out first what f of 0 and f of 1 are. So f of 0 would just be what we get from plugging in 0 into this function. So 1 minus 0 minus the cube root of 0, which the cube root of 0 is 0. So we're going to get 1 minus 0 minus 0, which is 1. Okay. And then f of 1 is just going to be 1 minus 1 minus the cube root of 1, which the cube root of 1 is 1. So we have 1 minus 1 minus 1, which is negative 1. So basically what we know is for any possible number we pick between negative 1 and positive 1, there has to be some x value that we could plug it into this function f of x in order to get that output out that we pick. Well, since we're trying to figure out, is there a place where this function equals 0, we can use the intermediate value theorem to say, well, yes, there must be a place, there must be an x value that we can plug into this function to get 0, because 0 is between -1 and 1. So as a result, we know that there has to be a root between this interval here. We don't necessarily need to figure out what it is. This problem does not ask us to do that, but we know that that root has to exist. We know that there has to be an x value where we can actually get 0 as an output, since it's between -1 and 1, and since we know our function is continuous on the interval 0 to 1. So that is all I got for you. I hope you found this video helpful. If you did, please be sure to hit that like button down below. It's a huge help to my channel, huge help to me. Allows me to keep making more videos like this, keep doing live streams like this. If you're liking the live streams, really be sure to hit that thumbs up button so I know you guys like them. Drop a comment, let me know as well. It's love seeing comments like that. So be sure to subscribe to my channel as well and hit that bell icon and turn on your notifications. I'm going to be doing some more live streams the next week or two because I know finals are coming up. So be sure that you're notified when I'm going live. So hope to see you back next time. Thanks and see you then.